Welcome to another math video. So this video would be about the union problem, which I myself framed in fact. So we are all familiar with the union operation in sets. We have something known as A1 union A2, which means we are talking about the number of elements which are there in the set A1 or the set A2, right? So in similarly, we also know about the intersection operation in sets A1 intersection A2, which means that the set of those elements which are there in both A1 and A2, that it is in union, it is or, in intersection, it is and. So this is the basic thing in union and intersection in sets. So the next thing uh, which you might be knowing is that the familiar formula for uh, the number of elements in A1 union A2 and the relation with this, that is n of A1 plus n of A2 minus n of A1 intersection A2. So this is another familiar formula. And what exactly is the proof for this? It's just a simple analysis by Venn diagrams. So we consider this to be our set A1, and let us say this is our set A2. Then that means that n of A1 means this whole thing, n of A2 means this whole thing, whole A2. But in calculating the total number of elements in A1 and A2, what we did was we calculated the sum of elements of A1 and A2. But one thing which we did was we over counted the central part. This part we over counted it because we counted it in A1 and A2 as well. So we need to subtract that. We need to count only once. So we subtract n of A1 intersection A2. So now we go further. What we usually do something like this, maybe trying to find out a formula for this. Even this is quite a familiar problem for maybe most of you who are seeing this video. So there was a formula for this, but I would be bringing about the derivation for this formula here. So this is nothing but n of A1 union A2 plus n of A3 minus n of A1 union A2 intersection A3 by just using this formula. What I did was I grouped these two. So this is n of A1 union A2, then n of A3 minus this intersection with this. Then we need to again apply the formula for this. So that is n of A1 plus n of A2, just about what we did, minus n of A1 intersection A2. 2 looks so. Yeah. Then this is what I used here. Then again plus n of A3. And here we use the distributive law. So we can write it as A1 intersection A3 union A2 intersection A3. So then we can write it as n of A1 plus n of A2. I'm bringing this here forward, plus n of A3 minus n of A1 intersection A2. Then again I here apply the above formula, that is n of A1 union A2 stuff. So that would be just n of A1 intersection A3. I'll put a bracket here, plus n of A2 intersection A3, this thing, and this thing. Now subtract the intersection of these. So that would look like what? That is A1 intersection A3 intersection A2 intersection A3. So if you do want brackets as well, you can put it like this. Yeah. So then we're almost done. So we have n of a1 plus n of a2 plus n of a3 minus n of a1 intersection a2 minus n of a1 intersection a3. Then coming down, minus n of a2 intersection a3. Then this becomes plus n of, we're taking intersection again, but a1 intersection a3 intersection a2 intersection a3 is nothing but just a1 intersection a2 intersection a3. Why do we need to include a3 two times when it's just intersection? So it's just this. So we've successfully derived the formula for n of a1 union a2 union a3. And this was pretty easy itself. So now, okay, fine. We did it for 2, 3. What about in general? What would be the formula for n of a1 union a2 union a3 up to an? Does there exist such a formula? Such a thought came into my mind. So just try to do it. So what we can do is to find patterns. We need to find patterns in several cases. We took like here 2, we did it for 2, we did it for 3, maybe try it for 4 next. And then after finding kind of certain pattern, we can claim that it's true and then prove it using induction. So that is what I intend to do here. Induction. Coming down. Yeah. So let's try for 4. So let us take 4 sets, A1, A2, A3, A4. So we have n of A1, union A2, union A3, union A4. Slightly more complicated, but not so much. So this becomes n of a1 union a2 union a3. I'll just take this part, then plus n of a4 minus n of a1 union a2 union a3 intersection with a4. Again, just apply the same formula if you see. So again, next we have this. We can just substitute the above formula, which we tried for 3. So this becomes this n of a3 minus n of a1 intersection a2 minus n of a2 intersection a3 minus n of a1 intersection a3. I should have written it here. Minus n of a1 intersection a3 plus n of a4 minus n of a1 intersection a4. This union with a2 intersection a4. This union with a3 intersection a4. That's more complicated, but doable. So then we have n of a1 plus n of a2 plus n of a3 minus n of a1 intersection a2 minus n of a2 intersection a3. Again, writing down the same thing, of course. Intersection a3 plus n of a4. Now, this is what I need to manipulate. So again, I do apply the same formula which we got for 3 sets. These are 3 sets in union. So I can apply the same formula again. So that becomes a1 intersection a4. Of course, I put a bracket here. Plus n of a2 intersection a4 plus n of a3 intersection a4. Then we have something like this. Yeah. So then we will have minus n of a1 intersection a2 intersection a4. I'm just writing a4 one time because it's just intersection. We need not write two times. So then similarly, we would have minus n of a1 intersection a3 intersection a4 and minus n of a2 intersection a3 intersection a4. Yeah, plus n of all that a1 intersection a2 intersection a3 intersection a4. Just writing a4 one time again because of the same reason. So we have this. Now we will try to group similar looking terms. That is what we are going to do. Yeah. So notice that there is n of a1 plus n of a2 plus n of a3 plus n of a4. These are one set of similar terms. Right. Then we have all this 2 taken. A1, A2, A2, A3, A1, A3, then A1, A4, A2, A4, A3, A4. All of these minuses, minus, minus, minus. There is a minus outside, so all these get a minus. So what do we have? We have this minus n of A1 intersection A2 plus n of A1 intersection A3 plus n of A1 intersection A4 plus n of uh, A2 intersection A3 plus n of A2 intersection A4 plus n of A3 intersection A4. All these with minus. Yeah. So these were the two things grouped together. But what about the three stuff? So essentially, I think I missed a term here. I did miss a term. Yeah. Because minus n of A1 intersection A2 minus n of A2 intersection A3 minus n of A1 intersection A3, there should have been a plus n of A1 intersection A2 intersection A3. Sorry for that blunder. Yep, now it's proper. Yeah. So there would be a plus n of A1 intersection A2 intersection A3 plus all these are pluses because minus into minus. This, and this plus n of A1 intersection A2 intersection A4 plus n of then we have A1 intersection A3 intersection A4 then a plus yeah, then a plus n of A2 intersection A3 intersection A4. So then the last term is 4 intersections with a minus. Minus n of A1 intersection A2 intersection A3 intersection A4. Thus, we are done with the entire formula. So this is the huge formula for n of A1 union A2 union A3 union A4. Big, yeah. You can realize the same thing by using Venn diagrams, but analysis by Venn diagrams becomes difficult because there would be so many regions you need to consider. So we resort to this kind of method to proving. So let us try to find out a certain pattern. Here, uh, in the first formula, we observe that there is a plus term and a minus term. And of course, like we take one set at a time, and then here we take two sets at a time. Coming to this formula. So this is like I can put a minus common here. So plus. So here I have a plus terms, minus term, and a plus term. Here I have taken one set at a time. Here I have taken two sets at a time. And here I have taken three sets at a time. What about for 4? Here as well. So initially there is a plus, then there is a minus, then there is a plus, and again there's a minus. And then I had taken one set at a time. Here I had taken two sets at a time. Here I had taken three sets at a time. And here I had taken four sets at a time. So there's definitely a pattern. And we are essentially getting all the possible two sets combination intersection. You could yourself check uh, by combinatorics because uh, you have a total of four sets, and how many ways can you choose two of them? Four choose two, that is six. So here there are six terms if you see, and similarly for others also it is true. So there's definitely a kind of pattern appearing here, and when you see this plus minus pattern, and we are taking two sets at a time, three sets at a time, four sets at a time, what does it actually remind you? It actually reminds you about polynomials. We had Vieta's relations in polynomials, where we have sum of roots taken one at a time, two at a time, then n at a time, and stuff like that. And we could actually generalize that for any n degree polynomial. So here also we are going to attempt to generalize it using induction. And many of you may ask, why is generalization important? Why do we need to generalize? Because it's just that it's harder than just trying for a particular case, like taking four sets or three sets or maybe five sets. Even five sets would not be difficult. Maybe you can try it yourself. But generalization is the hard part in you know, most of the math problems. So we're going to attempt, if possible, to try to find out a generalized version. And why a generalized version is important? Because it helps you to code it in computers. If you can code it using a programming language, my favorite is Python. So you can, in fact, easily try to find out values in real life using just that a code. When you run it, you get the output. To even write the code, you need a generalized version because you don't know what's the value of n. How many sets are there? We don't know. So we would naturally need something called as generalization. So here we are going to start generalizing the union. So yeah. So if we have this A1 union A2 union A3 all up to AN, by just a little bit of pattern matching, we get it is equal to this n of A1 plus n of A2 plus n of A3 plus dot 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 plus n of AN. Then minus n of A1 intersection A2 plus n of A1 intersection A3 all the way up to say n of AN minus 1 intersection AN. Obviously, there will be n choose 2 number of terms here. So yeah, and then it goes on. If we start writing this, it's going to take a lot of time. So we assume that this is in fact true, and we'll try to do it by induction. So we'll take this whole thing, uh, an plus 1. So this is just using the above formula, the first formula which we had for two sets. I can write this as n of A1 union A2 union A3 dot union AN plus n of AN plus 1 minus n of all these intersections, all these unions, sorry. This intersection with uh, AN plus 1. Yeah. And this thing, we know that it is this whole formula. You notice that here, all these terms will appear, and you know, here all those terms will appear and an an plus 1. So total of n plus 1 terms. So that means that the first part is at least true. Yeah. So then let us try to do this part. Again, using the distributive law, it's A1 intersection AN plus 1, this union A2 intersection AN plus 1, union, so on, up to AN intersection AN plus 1. So here you notice that there are again n sets in union. So we can naturally again apply that formula in the sense this one. So now what I do is I try to group those the ones in which there are two intersections. So here I get like this, like total of something like this: A1 intersection AN plus 1 minus n of A2 intersection AN plus 1 dot to, oh, sorry, it's a plus here because I've taken minus common, plus n of AN intersection AN plus 1. So these terms have to, uh, you know, actually be added to the ones here matched properly, like two intersections. So here I had already told you that there are n choose two many terms, and yeah, and here if you see I need to add a total of n terms. So what exactly is n choose 2 plus n? So it's just n times n minus 1 by 2 plus n. That would be n times n minus 1 by 2 plus 1. Yeah, that's just n times n by 2 minus half plus 1. So this becomes a plus half. So it becomes n times n plus 1 by 2. N times n plus 1 by 2. That is equal to n plus 1 choose 2, if you see. And that means even the second part, the, what do you say? The two intersection, that is AI intersection AJ for all I not equal to J, that part is also matching. That is for AN plus 1. So in the same way, you could see that there are actually, this thing is actually true for any n. If you take n of A1 intersection A2, sorry, n of A1 union A2 union A3 all up to AN, because you can do the same thing for intersection 3 taken 3 times, like AI intersection AJ intersection AK. Initially, you would have n choose 3 many terms, and here you would notice that there are, I think, I need to see n choose 3 plus. Here, if I take two intersections, there are again a total of n terms. Yeah, there will be n choose 2 terms. Sorry, yeah, n choose 3 plus n choose 2, right? Because there are n sets I need to take two of them. So uh, this is n plus 1 choose 3. By using a familiar formula, I don't know if you've heard of it, it's this n choose r plus n choose r minus 1 equals n plus 1 choose r. So if you see, this is a very nice result. And in one of the previous videos, I'd explained about something known as the combinatorial arguments in a digit problem video. So you could maybe revisit that and uh, just try to prove this combinatorial. And if you could do let me know in the comments. And yeah, so similarly, if I want for four elements, four intersections, that is AI intersection AJ intersection AK intersection AL. In the initial part, I would have n choose 4 many terms. I would have n choose 4, and it's here. If you see here, I need to take 3 because if I take 3, all have an plus 1, and rest 3 elements are selected. So then from these I have to select 3. So n choose 3. N choose 4 plus n choose 3 again becomes n plus 1 choose 4, which matches. So on up till n choose n plus n choose n minus 1 would give you n plus 1 choose n. So till that this is true because of this result. So maybe here I'm not writing it completely mathematically, but it's just the idea. This is the idea which I got. So writing it mathematically would take time. So you could maybe try to write it because this is the actual intuitive idea of why this n of a1 union a2 union a3 all up to an has that plus minus kind of alternating stuff, and also taking one at a time, two at a time, three at a time, four at a time, and so on. So yeah, this was it in the video. I hope you enjoyed the generalization. Of course, the initial part of the video was easy, more like a warm up, because it was just trying a particular case. But generalization needs more thinking. So even I couldn't get this straightforward. I had this video. I had this idea. I mean, just to make this video yesterday. So then I tried it for long, thought about it. Why could this be true? And certain ideas came to this mind. And this was what I felt was the most important step. Trying to see this, why it works for all. You take any number of intersection, maybe if there are n, and you're trying to see if it matches n of a1 intersection a2 intersection a3 all up to ak, where k is of course less than n. Then you need to analyze like this. You need to take k elements. So from the first, by assuming that formula, we know that there are n choose k, and from here I already know an plus 1 is fixed, and I need to select the k minus 1 other elements. So have n choose k minus 1, and by that combinatorics formula, or maybe I would say a theorem, um, we know that it's n plus 1 choose k, which again matches for n plus 1. So if it's true for n, it's true for n plus 1. You take any k less than n. Of course, k has to be greater than or equal to 1. So that means by induction, we have proved that that formula here, which I've written, I've not written the complete formula, but still, you know that it's true by induction. So this was it in the video. Thank you. Hope you all enjoyed the union problem created by me.